All right, so the next experiment we have is to determine the liquid limit and plastic limit of the soil, of the fine grained soil. And we've learned in class that that's the aspect of the engineering classification that we'll really need to understand because the amount and the behavior of the clay will really dictate the behavior of the soil altogether. The image on the screen here, as you can see, is a liquid limit cup that has already been tested. You can see that the groove has been closed by at least a half of an inch, and so hopefully they've counted the blow counts and seen that that is within the range that they need for the liquid limit test. Okay, so let's go ahead and take a look at our learning objectives. Obviously, we want to explain and determine the Atterberg limits of soil. Actually, just two of the Atterberg limits. We're not going to do the shrinkage test, which is a different type of test we'll talk about in a minute. This follows ASTM procedure D4318. We could first start off by saying that clay is obviously a little bit different material than sand and silt. Clay is defined as a material smaller than 2 microns. And unfortunately, sometimes quartz and feldspar and mica and some other materials can get smaller than that. But for the most part, that is a clay material. And that clay material often will dictate the behavior depending on the percentage that is in with the soil structure itself. And as I mentioned in class, a definition of clay or a behavior of clay is the particles have something called plasticity, which means it's pliable, movable. It is soft and it changes shape, but still holds together as a solid unit of structure. Where sand wouldn't do that, it would just fall apart if you try and move it and remold it. Plasticity is the term we use for that, and the plasticity changes in clay depending on the amount of water content in that clay. And like I said before, that the amount of clay within the soil structure will dictate the behavior, and clay dominates that behavior if you have 35 to 50% of the material being clay. Okay, so to reiterate the history here and the concept of the Atterberg limits, this was named after a hygronomist named Albert Atterberg, and he came up with the states of behavior of plasticity for a clay material. Actually, for all materials, um, but we know that sands and silts are typically not plastic in nature. So we call them non-plastic or non-cohesive or cohesionless because there isn't that attraction between particles that clays have. Clays have that attraction when water is involved to each other. And so the consistencies of the material, as you can see from this chart, show that the clay can range from a very solid state all the way down to a liquid state where it begins to flow. And what we want to determine is the range at which the clay will act in a plastic state, because for the most part, the water content of a soil material will be within this plastic range. If it is solid state, now we're into a cementatious, potentially rock, or very, very dry soil, and that can be not a very good base for a structure. Or if it's in a liquid state, the opposite range, that material can begin to flow and not have a good solid base to support a structure either. So we want to perform any design or construction around clay being in a plastic state. And what Atterberg did is he came up with these ranges and these limits. And so the shrinkage limit is the term at which the clay will begin to lose the majority of its moisture, and it would go from a semi-solid to a solid state. There is a test for that. We will not do that in our laboratory course. The next limit that he dictated was the limit at which the material becomes is between plastic and a semi-solid state. Okay, remember that these limits are the amount of moisture in the void space or the moisture in the soil, and then the limit at which the plastic and the liquid state range comes to meet is called the liquid limit. And remember, that is the moisture content. So from the chart on the bottom right, you can see that as the moisture content increases, the limits are changing. So we have a shrinkage limit, to a plastic limit to a liquid limit. And the important idea here is to understand that the plastic limit is the moisture content at which the material stops being pliable and begins to crack and become more of a semi-solid state. The liquid limit is the moisture content at which the soil starts to flow like a liquid and be less like a plastic. And so the range at which the material is plastic we call the plasticity index. And that is the difference between the liquid limit and the plastic limit. All right, so the liquid limit test, and remember that is where we look at the range at which the material becomes in a liquid state rather than a plastic state. So we want to determine the moisture content of the soil at the point where between the liquid state and the plastic state. It was developed by Arthur Casagrande. The process, and I'll go through this on the video, but coming up in a minute. But the process is to mix small grain soil. Actually, this says -200. What we typically do is we use -40 material for our test. So we take whatever soil we have, break that down into its smallest particles without breaking any sort of sand particles or gravel, and then sieve it through the number 40 screen and use any -40 material for this test. There's no need to have any sands because we're looking at the fraction of the smaller grain materials for this test. The first thing we want to do is mix it with water to form a consistency that looks like it's potentially flowing. It's still plastic, but it's potentially flowing. Then we place a layer of it in a brass cup. We place a groove through the center of that layer. We rotate the handle. Once we have that complete, we rotate the handle to drop that brass cup onto a hard rubber block until the groove closes by a half an inch long. And I'll show you a picture of that here soon. Now I want you to understand that we want to count the number of blows that we are applying to that soil. And we want to do this in a constant fashion where it's usually about a drop or two per second. Okay, and then you count the number of blows, and you're hoping that the number of blows is between 15 and 35, somewhere in that range. What you're looking for is 3 different ranges blows as that groove closes in. You repeat this test 2 more times for a total of 3 times, altering the moisture content to allow the ranges above, below, and near 25 blows. Okay, so it'd be good to have a range between 15 and 22, 22 and 30, 32, and then 30 to 35. Those are kind of the ranges you want your blows in. So if you start off with a little bit lower moisture, you'll be in the higher number of blows it takes to close that groove. And then as you add water, you will begin to get less amount of blows to close the groove. Once you have that, you determine the moisture content of each test. So you take a portion of that soil that's in the cup, place it into a small dish, weigh the dish, put it in the oven, and then weigh it again once it's dry. And once you have the moisture content versus the blow count, then you develop a plot to help you look at what the liquid limit actually is. Let me show you some pictures here. This is not a great picture. It's a brass cup. You saw a picture at the opening slide. And then you have a grooving tool at the bottom there. And you can see on the right that you place a groove through the soil, and then as you lift and drop that cup onto that rubber base, it will close up to be within a half of an inch, as you can see on picture D right there. So that's the liquid limit test, and I'll show you more about that on the video. Now we have the plastic limit test. That is the opposite range of the plasticity aspect of that clay. So with the plastic limit, you take the same soil that you had when you were doing the liquid limit test, -40 material. That says 200 on the screen, but it's typically -40 material, with a little bit of water, but not a whole lot of water like you did with the liquid limit test. This is obviously the opposite range, so you're looking for the soil to just be barely pliable, just have the consistency to be able to roll out or mold, but not quite falling apart. Then what you want to do is you want to take a small portion of that soil and you roll it out into 1/8 of an inch diameter strips or worms or whatever you want to call it. You roll it out with your palm, and then you want to have the consistency to where as the soil gets small enough to get to the 1/8 of an inch diameter, the strip starts to break apart and crumble at that diameter. If it's bigger, a 1/4 inch or less, it's not breaking apart. But when it gets to the 1/8 of an inch, that's when it begins to break apart. That means that the soil is beginning to be semi-solid, right at the edge of being liquid and semi-solid. Then you take those strips, put them in a container, put them in the oven, and get the dry weight the next day. And then that moisture content is indeed the plastic limit for that soil. Okay, and here's an image here of somebody doing this. You can see the strip there starting to break apart. You can see how it's not completely solid. You can see the little cracking in it, and it's on a this one looks like on a granite plate. We use glass plates with the rough side up, and I'll show you a picture of that here very soon. Once you have that information, where you've plotted the liquid limits versus the blow counts, and you determine what the liquid limit is at 25 blows, then you can calculate the plasticity index, which is the liquid limit minus the plastic limit, and then you have a range at which the plasticity is described there based on the plasticity index. You can also determine the liquidity index. That is just a value of the current moisture content and how it relates to the Atterberg limits. Okay, so you have just a simple range there of the current moisture content minus the plastic limit divided by the plasticity index. Okay, well, now let's get to the actual experimentation. All right, so here's what we're going to do. We have our liquid limit device, and I'm going to show you a real quick calibration. First of all, if you pull the pin out and remove the brass cup, you can see the base where that brass cup hits. And that pin that connects the brass cup to the frame itself becomes very important later on with our plastic limit test, but it just keeps it in there for the liquid limit. That is your grooving tool that you'll have, and on the back side of that grooving tool it is a specific height of drop that can be placed right where it drops, and you place the cup right on that, and then you move the rotating cam to where it just touches that cup, so the cup should not rise or fall when it's placed on that back side of that grooving tool. Okay, so it looks like that machine is calibrated. If it needed to be rotated, there are 2 screws at the top, one to loosen it and one to adjust it in and out to make it more solid. The rubber base is there. You have your 3 dishes to put the soil in. They're much smaller than the other, and you will get soil that is passing through the number 40 sieve, which you can see right there, placing in the cup. So you place a little bit of that in the cup, probably about half of that, maybe a little less than half. You see it's just a powdery form of the -40 material. Then you begin to mix water into it and mix it to where it's a complete consistent moisture content all throughout. So you don't want dry particles in one corner and wet in another. You want it to be completely mixed. So it takes a little bit of water to get this going, but you will find out that you'll get very used to it. And really, you want to start off a little bit drier and then work your way more wet, like I talked about in the previous presentation. It's very important that that the moisture content is consistent. So you see me mixing, adding water, mixing, adding water. I'm not going to show you the whole thing, but it is mixed to a point where I can start to begin to it starts to become pliable, movable, moldable, if you will. It's not in powder form anymore. Okay, so you can see me mixing. So now it's time to take some of the soil and place it into the brass cup. So you want to mold it and move it around in the brass cup to the base of it. Then you take your grooving tool and align up the top with the top cam area where the pin goes, and the bottom through the very bottom, and pull it through. And I want you to notice the grooves that it cut into the soil. That typically means that the soil is still too dry. And if you count all of these blows up here, I think I get to 40, and it doesn't close up that groove that's being placed through. Okay, I'll go ahead and count these up, and I think I stop at about 40. You want it to be 35 or less, and you could probably go to 50 and it doesn't close up. So go ahead and take that material back out of the brass cup and start again. And you want to make sure, though, that every time you remove any material from the brass cup, you clean it completely with a wet rag or wet paper towel. That brass cup needs to be perfectly clean and dry before each trial. Okay, and you'll see me get all the material out, and then add more water in, mix it up again, and then I'll try it again. Okay, and so I've got it ready. Again, I added more water and mixed it, and now we'll put another groove through it. Okay, and now let's go ahead and check it out. Okay, 1, 2, 3, 4, 5. And I want you to notice it's about 2 revolutions per second is what you want to do. Then I get to 40 again, and it doesn't close up. So I've got to try it one more time. So now I've mixed it again. Notice my brass cup is clean and dry between every trial. So we'll take a few paper towels. Now that's a little more liquid, we can go ahead and go through. Clean off your grooving tool, of course, each time as well. And then pass the tool through and make a groove again. And now this time I think it'll probably work. So about 30, and it got it. So now what we want to do, it created that 1/2 inch, so we cut a groove through the center and we collect all the material out of that. That's our moisture content. Place that in the little dish, and then we have it doing again. This time we've added more moisture to it again, and this time we want to be between about 22 and 30. 22 and 25 is really what we're looking for. Looks like we got 15 that time. So this must be my final point. So again, make 2 cuts through the center, collect that material, place it in the smaller dish, get enough material in there where you can get a good wet weight. Put the lid over it just while you're performing your test. Weigh it wet, then take the lid off and put it into the oven for drying. Get it in 24 hours. All right, now it's time for the plastic limit test. We take that same material, put it into our porcelain dish. Notice the glass plate there, and we want the rough side of the glass plate up. That's what we're going to use to make our plastic limit test. And now remember that the material that, or the water that you're adding to this material, is much less than the liquid limit. So you want it to be much more pliable, a little more solid material, and mix it again very consistently. You don't want dry and wet inconsistencies in your dish. Okay, you want it to be consistent. So it take a little bit to mix it up. Okay, so once you have it mixed up consistently, you want to go ahead and make sure, first of all, your glass plate is clean. And then you begin to create ellipsoid balls. Probably each person in your group can make one. And then you begin to roll it out with the palm of your hand. And you roll it on the glass plate until it gets to a diameter of about an 1/8 of an inch. Now you can see the little pin there from the liquid limit device. That's an 1/8 of an inch diameter. So that's what we use as a guide. Now that right there is smaller than an 1/8 of an inch, or about the same size. So if it can roll smaller than an 1/8 of an inch, the material is still too wet, and you'll have to dry it out. Usually a hair dryer will do. If it starts to crumble and break at that 1/8 of an inch diameter, that is the right moisture content for the plastic limit. See, I've separated the ones that are crumbling from the ones that didn't. So the ones on the glass plate have crumbled at that 1/8 of an inch, so I place those in the dish to get the moisture content from. The one that was smaller I don't use, obviously, because the moisture content was too high. And I do this again. Probably you need to do this twice to get enough material to get the moisture content. So that's why I'm doing a few more threads, because if you have too small of a sample, it won't read. But you can see that this is breaking up just fine right at that 1/8 of an inch diameter. I can use that as a guide. If it gets a little bit smaller, then I don't use that portion of it. Like that one piece there is probably a little small, so I'll take that off. The rest of it goes into the dish. Weigh it wet. Put the cover over it while I need 2 full dishes, so while I wait for the second one, and then put them both in the oven at the end. So this is just me doing another dish here. Okay, so you can see that some of the material is a little bit too wet. Most of the time, if it is too wet, you're going to have to take it, smash that back down, put a hair dryer over it to dry it back a little bit until it is the right moisture consistency. Okay, remember you want it fairly consistent, but sometimes you get some pieces that are a little wetter than others. You just don't use those. Okay, so those all work. Fill it back into the dish, and again get another weight. You want to get 2 dishes with enough weight that usually about 18 to 22 grams of soil in there is sufficient. That's why if everybody in the group does it, you should have 2 dishes fill, and then you take the average moisture content of the 2 dishes, and that becomes your plastic limit. Again, place it in the oven with the lid off, and get the moisture after 24 hours.